So in our last screencast, we learned how to work simple gas law problems by changing conditions. Here's the next step up. Namely, we have a gas and it has a pressure and a volume and a temperature given. And then we're told that the volume and the temperature are changed, and we want to know what will happen to the pressure. Well, this is really a combination of all the other gas laws, and some people like to use an equation called the combined gas law. P1 V1 over T1 equals P2 V2 over T2, and you put your initial pressure, temperature, and volume into this law, and the volume and the temperature of the changed conditions in, and solve for pressure. But of course that involves algebra, and it involves possibly making mistakes because units are not the same. So instead I'm going to approach it like I approach all the simple gas laws. I'm asked about the pressure. So we start with what we're asked for, the pressure. And the pressure initially was 3.00 atmospheres. But unlike the simple gas law problems that we did the other day where there was one changing condition, in this problem we have two conditions changing, but that's not a problem. We're just going to adjust twice for the changes in conditions. I always like to keep in front of me my relationships of pressure, moles, temperature, and volume. Because if the volume is going to change, it's important to know that the pressure is inversely related to the volume. So therefore, if volume increases, I must make the pressure decrease by the same proportion that the volume increased by 4/10. Then I move on to the change in temperature, and I have to think of this in kelvins, 303, and this in kelvins, 273. And I think how pressure is affected by temperature, and clearly that relationship is direct. And in this problem the temperature is decreasing. That would have an effect of decreasing the pressure as well. So I'll decrease the pressure by a further 273 300ths. Kelvins cancel, leaving me with a new pressure in atmospheres, and that new pressure is 1.80 atmospheres. In other words, by decreasing the volume and cooling the gas down, we have so decreased the force against the container walls that we only have 1/3 of the pressure we initially had. Now, as a second example of a very similar problem, if you've seen movies of divers, they release bubbles if they're scuba divers, and those bubbles rise toward the surface, and as they rise they seem to expand. And here again is a problem that can elucidate that using gas laws. If we released a bubble having this volume, when it's under a pressure of 3.6 atmospheres, which it would be in a deep lake, say 100 feet or so, at a temperature that's given, kind of cold, but that's true of most lakes, it's coldest at the bottom, the bubble rises, and as it reaches the surface the pressure changes and the temperature changes. So again, I'm going to have to deal with changing conditions. First, a little bit of preparation, in that I can't use Celsius temperatures when I'm doing gas laws. This should actually be recorded as 277 K, and this one as 296 kelvins. And the other problem I see in this particular instance is the first pressure is given in atmospheres, whereas the second pressure is given in millimeters of mercury. And of course, if we're doing this by ratios, we won't have consistent units. So we have to convert one pressure to the other units. And it doesn't matter if I convert the millimeters of mercury to atmospheres or vice versa. I'm just going to go ahead and convert 755 millimeters of mercury to an atmospheric pressure. Of course, 1 atmosphere is equal to 760 millimeters of mercury, meaning that the actual pressure we should use is 0.993 atmospheres. So yes, I want to think of this pressure as being 0.993 atm. Now we're ready to do the problem, because with consistent units of pressures and temperatures, we can see what changes are occurring. Once again, I'm going to focus on my relationships, and I'm going to start with what I'm asked for, the bubble's volume. So I'll take the 2 centimeter cube volume that was the initial volume, and I will make 2 adjustments, one for temperature and one for the change in pressure. Let's do temperature first. There's a temperature-volume relationship here. It's somewhat obscure because they're both on the same side of the relationship. But if I multiply both sides by volume, the volumes would cancel from the right side, and now I see that volume is in direct proportion to temperature. There's a direct relationship. So in this particular problem, the temperature is increasing as the bubble rises, so that should expand the bubble, make it increase by 296 277ths. And we can cancel kelvins. And then when I want to think about pressure and volume, I go back to my initial relationship. I know that pressure and volume are indirectly related. And in this problem, since the pressure is dropping almost 4-fold, that's going to have the effect of increasing the volume almost 4-fold. So I will write the ratio as 3.6 over 0.993 so that the volume increases proportionally. Then I grab my calculator and I calculate the final volume of the bubble as it reaches the surface to be 7.75 centimeters cubed. In other words, our bubble's volume has almost increased 4-fold, rising from the bottom of a cold 100-foot deep lake to the surface of that lake. Now, as another example, we've seen 2 changes in a couple of problems, but now look at what we've got. We have a molar amount of a gas, we know its volume, we know its temperature, and we know its pressure. And in this problem, we're going to change the pressure and change the volume and change the temperature and see what effect that has on the number of moles of gas. So I am going to go ahead and prepare before I start to solve. First of all, kinetic theory insists that we use kelvins for our temperatures, 293 kelvins, and the initial temperature was higher, 313 kelvins. And due to the inconsistency again in the units of millimeters of mercury and atmospheres of pressure, we have to make a quick conversion. 391 millimeters of mercury. If 1 atm is the equivalent of 760 millimeters of mercury, it means that the initial pressure is 0.514 atmospheres. So I cancel this and realize that is in fact the initial pressure. Now I'm going to start the same as I have started every problem. I'm going to start with what I'm asked about, and I'm asked about moles. So I start with the initial 0.8 moles of gas that we had. But since 3 changes occur in volume and in temperature and in pressure, all 3 of those changes will affect the number of moles of gas. Again, I'm going to have steadfastly in front of me my relationships so that I can visualize them. And first, if we're interested in how moles and pressure are related, that's easy to see. It's a direct relationship between pressure of a gas and moles of a gas. In this particular problem, the pressure is increasing from 0.514 to 0.855. So I need a proportional increase in moles of my gas. Atmospheres cancel, I still have moles. Now the other 2 relationships between moles and temperature and moles and volume are a little bit more obscure. So I remind myself that if I want to compare moles and volume, I should move volume to the other side of the expression. And I can accomplish that by multiplying both sides by V. And now I see that moles and volume are in direct proportion to one another. That's actually something called Avogadro's law. Volume of a gas and the number of moles of the gas are directly related. So if the volume is increasing from 40 to 50 liters, that would have a proportional increase in the number of moles involved. And we're almost there. The last thing I need to worry about is how how temperature is related to moles of gas. And they're on the same side, excuse my little touching the wrong button, because they're on the same side of the expression. I need to move temperature to the other side to get a clear view of what's going on. And I could do that if I were to divide both sides by temperature. Divide by T, divide by T, temperatures cancel. Now I see the relationship between moles and temperature. Clearly it's indirect. Namely, if the temperature were to decrease, the moles would increase, and vice versa. In this particular problem, the temperature is decreasing. So that should have the effect of increasing how many moles I have. So I put the larger over the smaller to get a ratio greater than 1. And everything cancels, and it leaves me with moles. I multiply it all out, and I get 1.78 moles of gas. But I need to read carefully. This is not really the answer to the question, and that's because we were asked how many more moles of gas must be added. So if we started with 0.8 moles, and through all these changes we end up with 1.78 moles, the difference is how much we had to add. And therefore, if I subtract 0.8 moles from what I ended up with, I realized that we had to have added 0.98 moles of gas. That's my answer. Now, in order to do the ideal gas laws that we'll address next, we need to know something about what's called STP, standard temperature and pressure. Because when I see the words STP in a gas law problem, I know I've really been given a temperature and a pressure. I just need to know what they are. And that's not difficult to remember. Standard temperature for a gas is 0 degrees Celsius, 273 kelvins. And it's logical that standard pressure, the pressure we use as a standard, would be 1 of our atmospheres of pressure, 14.7 psi, 760 millimeters of mercury, etc. And there's a very important fact that you need to know, and that is what molar volume is for a gas. And this is literally the volume that a mole of gas would occupy. And at standard conditions, and only at standard conditions, the volume of any mole of any gas is 22.4 liters per mole. You take any gas you want, and it would occupy a volume of 22.4 liters if it were under these conditions. Of course, this volume would increase if, say, the temperature were to increase or the pressure were to decrease. Molar volume is nothing really special. It's just a volume of a gas. It would change. But it lets me easily answer this question. What is the mass of a sample of oxygen that is 30 liters in volume at STP? So I know I have this available. And I'd start with the answer. Well, the molar mass of oxygen is 32 grams per 1 mole. That's molar mass. And that's essentially what I'm looking for. All I have to do is cancel moles, and moles can cancel moles if I invert and multiply by the molar volume, which I can do because the problem is at STP. And that introduces volume units, but those can be canceled by the volume units given. We're given 30 liters of gas. And everything cancels, and we get the final answer of 42.9 grams O2. So, there are further uses of the simple gas laws.